Okay, so this is the video for section 6.2. We make sure that during this lesson you have your fancy schmancy TI-83 or TI-84 calculator available. You're going to be learning some new stuff on that. We're going to be talking about binomial distributions. So we're going to first determine whether a probability experiment is a binomial experiment. Then we're going to compute probabilities of binomial experiments, compute the mean and standard deviation of binomial random variables. We're not really going to graph the binomial probability distribution, but we're going to talk about what a graph would look like and how to determine if it is bell-shaped. Because as you remember, in order to use the empirical rule, it requires a normal distribution that it's not skewed left or right. So we need to determine if it's a normal distribution in order to do the math that we're doing. So that's what we're doing 6.2. So let us jump in. So in order for a binomial probability experiment to be a binomial experiment, these things have to be met, these conditions. So first, it needs to be performed a fixed number of times. You have to have a fixed number of trials. So somewhere in the explanation or in the story, the problem, it needs to give a certain number of trials. So it might say that a dice was rolled 20 times, or 15 people were drawn from a certain population, or whatever. There needs to be 15 people were chosen at random. It needs to be a certain number of times. The trials have to be independent. We talked about independence before. The outcome of one trial cannot affect the other trials. So if I have a deck of cards and I want to pull out 4 cards from that deck of cards, once I pull the one, and I'm checking if I get a queen. So when I pull one card out, if I leave that card out, the probability of getting a queen changes. So therefore, each one is not independent of the other. But if I have 4 different decks of cards and I pull a card out of each of them, the outcomes do not affect each other, and so those would be independent. So they need to be independent trials. So remember before we talked about independence, and we talked about the probability of a woman surviving the year, and if it was a random one drawn at random out of the U.S., it's different than two women in the same apartment building. Those wouldn't be independent because their lives could affect each other. So remember that's independence is important. And for each trial, there needs to be 2 mutually exclusive outcomes. One is a success and the other is a failure. So if I'm rolling a dice and I'm looking for the number 2, then I'm either going to get a 2 or I'm not going to get a 2 on each roll. So it's either going to be a 2 or it won't be a 2. And then the probability of success is fixed for each trial of the experiment. So the probability can't change. And so if I roll a dice, the probability of getting a 2 is always 1/6. It never changes on that particular dice. The probability stays the same. Okay, so those are our 4 requirements. So let's test you on this a little bit. Just a second. I forgot this slide was there. You would think I would remember. So here's the notation that we're using during a binomial distribution. So there are n independent trials. So the number of trials in our experiment will be denoted by n, by the letter n. P is going to denote the probability of success. 1 minus P is the probability of failure. So if I have a 55% chance of, maybe I'm really good at bowler, I have a 55% chance of bowling a strike, then I have a 45% chance of not bowling a strike. X is the binomial random variable. So whatever that variable it is, whatever we're talking about. So in 6.1, we talked about the number of movies streamed on Netflix each month. So that would be our random variable. That's not binomial because there's not just 2 outcomes. But if I said the probability that the person viewed 3 movies on Netflix last month. My random variable would be viewing movies on Netflix. How many people viewed 3 when I drew 20 people out of 100, out of the population. Whatever, you'll see. We'll do some examples. Sorry, that was a really bad one. And so basically our number of successes, because X is the number of successes, our number of successes has to be in between 0 and the number of trials. So if I drew 4 cards at random, a card at random out of 4 different decks, and the probability it's a queen. So if I'm either going to have 4 queens or 0 queens or a number in between. I'm not going to have more than 4 queens because I only took out 4 cards. I'm not going to have less than 0 because that's weird. Okay, let's take a look at some examples and see if we can recognize a binomial probability distribution. I recommend keeping this list or this list right here handy in order to determine it, or if you have that PowerPoint up, you can flip back. So let's take a look. So here's the first one. Is this a binomial experiment? A player rolls a pair of fair die 10 times. The number X of 7s rolled is recorded. So we rolled the dice 10 times. We recorded the number of successes, the number of times we rolled 7. Okay, let's take a look. Yes, it's a binomial experiment. So the way that we know that, because our trials, we have 10 times. So we rolled the dice 10 times. So that's a set number of experiments. So it's a fixed number of times that we rolled the dice. So the trials are independent. Rolling the dice one time, or each time you roll the dice, does not affect the other times that we rolled the dice. There are 2 mutually exclusive outcomes, so it's either a 7 or it's not a 7. And the probability of success is fixed, so it's always 1/6. Oh, well, I don't know how big this die is. So, because, it's a pair of fair die. Sorry about that. So whatever that probability is for rolling 7 on a pair of die, it doesn't change. Okay, let's look at the next one. The 11 largest airlines had an on-time percentage of 84.7% in November 2001. According to the Air Travel Consumer Report, in order to assess reasons for delays, an official with the FFA randomly selects flights until she finds 10 that were not on time. The number of flights X that need to be selected is recorded. All right. Is this a binomial probability? I can't even speak, sorry. Is this a binomial probability experiment or not? It is not. There are not a fixed number of trials. I need to get rid of that yellow pen. There are not a fixed number of trials. Because we keep drawing until we get 10 that are on time, they were looking for 10 successes. They weren't looking for a certain number of trials and then counting the successes. They were counting the number of flights that they had to succeed. They were determining the number of trials based on how many successes they wanted to find. So that was the difference there, is that they didn't have a fixed number of trials. They had a fixed number of successes they were looking for. Okay, so let's go on to the next one. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females is selected is recorded. So let's stop and think about this a little bit. Is this a binomial experiment? Go through those 4 things in your head. It is not a binomial experiment. These trials are not independent. Once I take one person out of the class, the probability that it changes the probability of the next one being a female. Because I've taken one out, now there's only 29 kids in the class. So you could say the trials are not independent. They aren't, but also the probability of success is not fixed. Hoping that made sense for you. Hopefully that helps you. Let's move on. Okay, so we are going to be constructing a probability distribution, and we'll talk about what that means. I am not going to make you do a tree diagram. They're very involved. They take a lot of paper, but I want you to see why we do why the probability works the way it does. And this is going to go back a little bit to chapter 5, I think it's section 5.3, where we were multiplying probabilities. This is kind of going to go back to that so that you can see where that math comes from a little bit. So let's take a look. So 7% of the people in the US have blood type O negative. A simple random sample of size 4 is obtained, and the number of people X with blood type O is recorded. We're going to construct a probability distribution using a tree diagram. Okay, so each trial is pulling one person out of a hat or out of the population, which would be the United States. Okay, my first trial, I chose one person. It was either a success or a failure. They either had type O negative blood or they didn't have type O negative blood. One or the other. The next trial, I either end up with 2 successes, like right here, I could have 2 failures, or there's 2 different ways that I could have 1 success and 1 failure. Third trial, so here I could have, let me erase all of this. Here I could have all 3 successes, all 3 are failures. I have a couple of different ways that I could have 2 successes and a failure. I have a couple of different ways I could have 1 success and 2 failures. 1 success and 2 failures. So you see all of the different combinations I have here. So let's go to my 4th trial. Here's my, oops, I'm having issues. There's my 4th trial. So there are several different ways that I can do all of that. Let me actually do the math for you. So here's my different outcome. So the top one is 4 successes. Then I have 3 successes and a failure. There's a 3 successes and a failure in a different order. 2 successes and 2 failures. 3 successes and 1 failure in a different order. So here's all of my outcomes, and all I did was count the number of successes. So the ways that we can have 3 successes, there's 1, 2, 3, 4 different ways I can have 3 successes. Sorry about that. And the number of ways I can have 2 successes, there's 1, 2, 3, 4, 5, 6. There's 6 different ways I can have 2 successes. Hopefully that makes sense for you. So I'm going to actually build my probability. I'm going to build my table. I'm going to build my probability distribution table, my binomial distribution table. So I'm going to compute the probability for each of these. So 0 successes. So the probability of 0 successes, there was only one way that I could have 0 successes. Remember, if the first one was a failure and the second one was a failure and the third one and the fourth one. So remember, these are and. Because they're and, I multiply their probabilities together. So 0.93 times 0.93 times 0.93 times 0.93. It gave me 0.74805. So when it's an and, we multiply it together. So let's take a look at ones. So there's 4 different ways that I could have 3 successes and 1 failure. There's 4 different ways that can happen. So 4 ways that I could do 3 successes and then 1 failure. So that probability is 0.22522. So I have basically, hold on here. Here is my, right there is 3 successes and 1 failure, and I just multiplied that whole thing by 4 because there's 4 ways that I can do this. So let's look at 2. So I have 1, 2, 3, 4, 5, 6. So I calculated the probability of 2 successes and 2 failures, 0.93 squared and 0.07 squared. Then I multiplied it by 6. And I just did the other 2. So this is my probability distribution table. This is how I can determine the probability for the random variable x for each of these outcomes. I'm not going to make you do this. I just wanted to see where it comes from, where these probabilities come from. It's a whole lot of work. When I took probability, they made us do a whole bunch of these, and they were not fun. Okay, so let's move on. A binomial probability distribution function. This is really, so we're determining the probability of obtaining X successes, so a certain number of successes, in N independent trials. So when we know the number of trials, we know how many successes we want. This is called a combination. We do combinations and permutations. With combinations, order doesn't matter. So all of these, so back here, all of these are going to hold the same value. All of these are going to be the same. Sometimes order matters, and those are permutations. We are not doing that this term. You may do that if you go to 244. So in your calculator, you hit the second key. So the second key is on the very top left, right above alpha. And then you hit the vars button. Now the vars button is below where those little arrows are that you use to scroll, right next to program and clear, right next to your clear button. That's vars. Then scroll down to binomial PDF. I'm going to go into this a little bit more on the next slide, so if you don't want to go down there, that's fine. The first number right here, this is trials, whatever your number of trials is. This right here, P, is the probability of success. And then X, this is number of successes. So when you put this in your calculator, you're going to determine the probability of a certain number of successes when you have a certain number of trials, given that you know that the probability of a success. So let's do an example here. First though, sorry about that, math symbols. So this is just a good reminder of what these math symbols mean. So this is at least, greater than, no less than, or greater than or equal to. So this would mean if I said X is greater than or equal to 3, 3 is included. So 3 is part of your answer. X can be 3 or it can be greater than 3. So with this, more than or greater than, so if I have X is greater than 3, 3 is not included. You cannot include 3. That little line underneath means or equal to. So this is just a little word bank, a reminder of what these mean or what words you'll see in a word problem that will prompt you to use these. Okay, so let's actually do a math problem now. So according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability exactly 5 have 3 or more cars? So you are going to use the binomial PDF in your calculator. This means binomial probability, I can't spell, probability distribution function. That's what PDF stands for. Binomial probability distribution function. I'm erasing all of that. So once again, the 20 is the number of trials. So we sampled 20 car owning households. 30.35 is our probability of success. So you need to convert that to a decimal. And 5 is how many successes we want. We want to know what is the probability of exactly 5 successes. Exactly 5 people have 3 or more cars. So let's take a look at what that's going to look like. This is my answer. I'm not making you do this particular math right here. We're going to use our vars function, our binomial PDF function. Okay, so when you are in your calculator, you'll hit the second and then vars. So hit second vars, and then you will scroll down till you get to the A. Binomial PDF, that's at A. So binomial PDF is what you're looking for. So I have my on-screen is a TI-84. So what it's going to look like when you put that in, it's going to show you trials. Whoa. Sorry about that. Trials, P, and X value. So your trials is 20. P is the probability, the 0.35, and the X value, that's the number of successes. You put in 5. If you have a TI-83, you're going to have to put it in like this over here. When you go down to paste, hit enter. You might have to hit enter a couple times. You'll get the answer right there. That is the answer. So if you're showing your work on a test that you have to upload, I want you to write down Binomial PDF and write those values in there. I want to see what you put in your calculator. That is required. If you don't show that, you will not get full credit. Okay, moving on. Let's do another example. This one's a little bit different. In a random sample of 20 car-owning households, what is the probability that less than 4 have 3 or more cars? Now you could use your Binomial PDF and you could do the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. But why would you do that? Instead, let's take a look at Binomial CDF. This C stands for cumulative. Cumulative. It stands for cumulative. This gives me 3 or less. So if I have 0, 1, 2, 3, these are the people that I've drawn, 5, 6, these are my samples. Whoops, sorry about that. I want the probability that 3 or fewer have 3 or more cars. Less than 4. Less than 4. Since it's less than 4, 4 is not included. So I want 3 or fewer. I want to know 0, 1, 2, or 3. This will give it to me. The Binomial CDF will give me 3 or less. So let's look in a calculator. So once again, you do second vars. So you're going to do second vars. Then you're going to go down here to B, Binomial CDF. This is the one that's going to give you the 3 or fewer. So if it says less than 4, do not put 4 here. Do not put 4 because it is less than 4. 4 is not part of your answer. So I want to look at what I put in. Same thing, 20, 0.35, and 3 because I want 3 or less, but this is a CDF. So once I hit enter on my calculator, I'm going to get about the 0.0444. Let's do one more. This is hopefully not going to mess with your brain a little bit. So let's do one more. So let's take a look at this. So this right here says, in a random sample of 20 car-owning households, what is the probability that at least 4 have 3 or more cars? So once again, I'm going to write these down. So 0, 1, 2, 3, 4, 5, 6, 7, on and on and on. So if at least 4, I want these right here, right? I want not 0, 1, 2, 3. I want not that. Remember when we say we want not something, we do the complement of that. My Binomial CDF cannot give me 4 or more, but it can give me 3 or fewer. So I can do the Binomial CDF here, and I can do 1 minus to give me not 3 or fewer. So if I say at least 4 have 3 or more cars, this number can't be 4. So if I said at least 7 had 3 or more cars, this number here would be 6. It would be 1 less than that number. It's really important because it's not 0, 1, 2, or 3. So go ahead. I'm going to show you on the calculator what this looks like because there's a certain way that you need to put this in the calculator, and then we will come back and do some more math. Okay, so let me show you how we're going to do this on the calculator. I want to do this 1 minus Binomial CDF on the calculator. There's a couple of different ways that I can do it. One way that I can do it is I can just go into my second vars and go down to the 1 Binomial CDF and put in the 20.35 and 3 in there and go down to paste and get my answer, and then do 1 minus second answer. This little answer right here, you can bring up the answer from your previous from the previous problem. Right here, if you do second and then the negative sign, you see the answer is right above it. And that does 1 minus the previous answer. The other way to do it is to do your 1 minus and then do second vars and then go down to binomial CDF. I put in my 20, my 0.35, and my 3, and it brings that with it. So 1 minus binomial CDF 20.353 gives me that same answer. So those are the two different ways that you can do that on the calculator, and that gives us what that probability is that 4 or more people will have 3 or more cars. Okay, so hopefully that made sense. Now, what I would like you to do, I would like you to do A, B, C, and D on here. D you might struggle with a little bit, but at least attempt it. So pause this video and do A, B, C, and D, and then come back and we'll do it together. Make sure you are writing down your work, writing down what you put in the calculator. Okay, hopefully you did this one. So first we have exactly 5 are wireless only. So when it is exactly, we use binomial PDF. And then we will say, because we have 20 households, that was our sample size. The probability a household is wireless only is 0.41. And then we want to know at the probability there's exactly 5. So this would be the work that you would show if you were taking a test. That would be the work that you would show me in order to get full credit. Because if you do not show me work, you will not get full credit. So that probability, you should have gotten 0.0656 approximately. So now we need fewer than 3 are wireless only. So I want to know that the probability X is less than 3. It is not less than or equal to, it is less than 3. So I would do binomial CDF, because it's a cumulative, 20.41, and then 2, because it's less than 3. 3 is not included, so I need 2, 1, or 0. So once again, binomial CDF, not PDF, binomial CDF, 20.41 and 2. And that gives me about 0.0028 approximately. So how about at least 3 are wireless only? So I need the probability X is greater than or equal to 3. So that is the probability of not 2 or fewer, not less than 3. So basically, if I just do 1 minus 0.0028, I will get 0.9972. Or you could have done 1 minus binomial CDF 20.412. Okay, so how about this last one? I want to know the wireless only are between 5 and 7 inclusive. That means 5 and 7 are included. So let me just put some numbers here. 2, 3, 4, 5, 6, 7, 8, 9, and then on up to 20. Okay, we want to know between 5 and 7 inclusive. So I want to know this group right here. So a way that I can get this group right here, I'm going to use my trusty highlighter. I can find 7 or fewer. I can find all of this, right? Once I find all of that, I can find all of this right here. That's not a good number. That doesn't help me to see it very well. I can find all of this right here and subtract it. So what I would do, and you can put all of this into your calculator at once. I would do binomial CDF 20.41. 7 is included, so we want 7 on there, 7 or fewer, minus binomial CDF 20.41 4. Because 4 is included in what we are subtracting, I would use 4. So let me put that in my calculator, which I should have already done that, but I didn't. So sue me. 7 minus binomial CDF 20.414. You'd put all of that in your calculator, and I got approximately 0.3381. So I got approximately 0.3381, and that is my answer. Right, if you have questions on this, make sure you send me a message or an email, and I'm happy to help you. If you can say, the example at so many minutes into your video, or the example on slide 15 is really good because you can see the slide number on the top. Any of that really helps me to know exactly what you're talking about. All right, so let's continue. Let's talk about standard deviation. So I mentioned in the last video that we are going to learn many different ways to calculate mean and standard deviation, or expected value and standard deviation. So this is for a binomial random variable. Make sure in your notes you are clearly marking what this standard deviation is for. It is for the binomial random variable, and it's the standard deviation for that. So remember that n is the number of independent trials and the probability of success is p. So in order to get mu of x here, we multiply the number of trials times the probability of success. In order to find the standard deviation, we do the number of trials times the probability of success times the probability of failure, then take the square root of that. And this will give us our standard deviation. I'm hoping an example will help you out. Let's move on. Let's do an example here. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and the standard deviation of number of car-owning households that will have 3 or more cars. So we take the number of trials times the probability, and that will give us that gives us 140. So the mean is 140. So standard deviation. So this is how many we would expect. That's what we're saying. We say we expect there to be 140, because 35% of 400 is 140. That's where we got the mean. We would expect there to be 140 of these car-owning households would have 3 or more cars. So let's take a look at the standard deviation. So we'll take the square root of 400, times the probability of success times the probability of failure. And so I'm going to do that on my calculator. So this is the square root of 91. So that's approximately 9.54. Oops. So my standard deviation is about 9.54, and my mean is 140. Okay, so for a fixed probability of success is p, as the number of trials in the binomial experiment increase, the probability distribution of the random variable becomes bell-shaped. So as the number of trials gets bigger and bigger and bigger, we're going to become bell-shaped because we expect, about the dogs, we expect the number of successes to approach the mean. So because of that, it becomes bell-shaped. So what we do is, as a general rule of thumb, and this is something we are going to be using a lot this term in other ways, a way that we can tell if a probability distribution is about bell-shaped, if it has a normal curve, if it is not skewed, we use NP times 1 minus P. If that number is greater than 10, we can say that it is approximately bell-shaped, that it has a normal distribution. So this is just the stuff that was underneath the square root in the standard deviation. So looking back here, so NP times 1 minus P, this was underneath my square root. So it ends up being 91 here. Because that number is greater than 10, we can say that that is approximately bell-shaped. If that number was less than 10, we would not be able to say it was bell-shaped, and most likely we would be able to have to use a different method. But if I don't ask you to tell me if it is, and I just say, hey, do this math, just assume that it is. All right, let's move on. So using the empirical rule, so in order to use the empirical rule, we need our data to be bell-shaped, and that's one reason we check that. So in order to identify unusual observations, we can use the empirical rule. So remember that that is that the 95% of all of our observations are within 2 standard deviations of the mean. We've been already talking about this for a couple of weeks. So therefore, anything that is outside that 95% will be unusual. So if you see a probability that is less than 5%, that will be unusual. So if that is less than 5% is unusual. One more time, less than 5% is unusual. Let's do a couple of examples. We are almost done with this. Okay, this is the data we just did. So we got that our mu was 140 and our standard deviation was about 9.54. So a researcher believes that the percentage of that reported by Experian Automotive is wrong. He believes that the percent should be higher. So he conducted his own simple random sample of 400 car-owning households. He found that 162 had 3 or more cars. We want to know if this result is unusual. I'm going to give you 3 different ways to determine if this is unusual. You choose which one you like. We know 2 of them. Actually, we know all 3 of them already. The first thing I'm going to do is I'm going to take 2 times the standard deviation. So I'm going to take 2 standard deviations and add it to the mean. And that gives me 159.08. That number right there is less than this number. So that means that this one is more than 2 standard deviations away from that mean. The next way that I'm going to do it is I'm going to calculate the z-score. So I'm going to take 162 minus, so 140 over 9.54. So 162 minus 140 divided by 9.54, that gives me 2.31 approximately. So this is my z-score. Because that z-score is larger than 2, that means that it's more than 2 standard deviations away from the mean, and therefore unusual. Next, I'm going to do Binomial PDF. I have 400 households. The probability of success of having 3 or more cars is 0.35, and we want to know the probability of 162 successes. We want to know the probability that exactly 162 had exactly 162 of those car-owning households. Hold on a second here. I'm trying to talk and calculate at the same time, and it is not working well. Okay, so my answer here was 0.003. So that is definitely less than 5%. So since this is less than 5%, that also confirms that that is an outlier, that that is an unusual result. So those are 3 different ways that you can calculate that. So on this last screen, I want you to go back to the wireless only households problem. I want to remind you that there's 41% of all homes are wireless only. So I want you to calculate the mean, calculate the standard deviation, and use one of our methods to determine if it is unusual. Or you can use all 3 if you want to practice. So go ahead and pause this and then come back and we'll do it together. All right, so hopefully you finished that. So we have 300 households. So in order to calculate the mean, I did 300 times 0.41. So 300 times 0.41. So my expected value, I would expect 123 out of those 300 to be wireless only. Now I need the standard deviation. So I would do 300 times 0.41 times 0.59, and then take the square root of that. So I got approximately 8.52 as my standard deviation. So let's talk about those three methods. So I could do 2 times 8.52 plus 123. So 2 times 8.52 plus 123, that would be 140.04. This number is smaller than that one, therefore that one is outside the 2 standard deviations. Let's look at the z-score. So do 143 minus 123 divided by 8.52. So 143 minus 123 divided by 8.52. Whoa, that was weird. This is good to know when your calculator gives you a weird answer, when you did something wonky. So this is about 2.35. So that's my z-score. And once again, that is larger than 2. So that leads me to believe that or shows me that it's an outlier. Then we can do binom PDF 300.41, 143. And I would do 300.41, 143. And that gives me, that's funny that it gives me about 0.003 again, which is still less than 5%. If I was in class right now with you face to face, I would say, which one is your favorite way to calculate whether or not this is unusual and why? Thank you. And if you have any questions, send me a message, post on the forum, send me an email. Thank you.